In recent years, the intersection of computer vision and natural language processing has witnessed a remarkable advancement, so which is giving rise to innovative applications such as image captioning. So, this image captioning models have evolved from traditional approaches to sophisticated multi-language or multi-modal language models, which is blending the prowess of both vision and language understanding. So, today we will delve into the realm of this multi-modal language models and will explore their architecture, highlighting how they have revolutionized this image captioning. Right? So, let's start with understanding what is image captioning. So image captioning is a challenging task which involves generating descriptive and contextually relevant textual descriptions for images. So early image captioning models often relied solely on computer vision techniques, but they struggled to capture the nuanced semantics and relations which is present in the image. So the integration of natural language processing into this image captioning marked a paradigm shift, leading to the development of more robust and context-aware models. So there entered this multimodal language models, so which is inspired by the success of large language models like OpenAI's GPT, that is generative pre-trained transformer, which will leverage the power of both visual and textual data. And these models are trained on massive data sets that includes this paired images and captions, which is enabling them to learn the intricate connections between the visual features and linguistic expressions. So like this. Now, what is this architecture of multimodal language model? So basically, this architecture consists of two main components. First is a vision model and second is a language module. So let's explore. So what is a vision model? So in this vision model, we have a pre-trained convolutional neural network where this vision module often incorporates a pre-trained CNN such as ResNet or VGG in order to extract this high-level features from this input images. These features capture information about objects, their shapes, and spatial relations between the image. Then we have a fine tuning layer. So this extracts these visual features which are then passed through a fine tuning layer that adapts the generic features to the specific task of image captioning, which allows the model to focus on relevant details and discard the irrelevant information. Then we have some language modules, which includes the transformer based architecture. So the language module is inspired by the transformer architectures, which is similar to those used in state-of-art models like GPT. It comprises multiple layers of self-attention mechanism, allowing the model to capture long-range dependencies and contextual information from the textual input. Then we have a joint embedding space. So the visual features and this textual embeddings, they are projected into the shared multimodal space where the model can learn the alignment between the visual and textual representation. So this joint embedding space facilitates the fusion of visual and linguistic information. So how this multimodal large language models work? So we can understand that the working mechanism of this multimodal language models, it involves a seamless integration of the visual and the textual information in order to generate the coherent and contextual relevant captions. So it includes the processes like input processing, that is an input image is fed into this pre-trained CNN, extracting the visual features, and this input caption is tokenized and embedded using this language module. Then we have feature fusion, that is this visual features and textual embeddings are projected into a joint multimodal space. So the model learns to align these representations, capturing the semantic relationship between the visual and textual elements. Then we have a caption generator. The fused representation is used to generate a caption throughout autoregressive decoding, considering contextual information and learned associations. So this generated caption is refined iteratively, ensuring coherence and relevance. And then we have a training and fine tuning. So the model is pre-trained on large scale data sets, learning generic features from both modalities. So the fine tuning is performed on task specific data sets to adapt the model to the nuances of image captioning. So we'll avoid implementing this image captioning model, but there are the codes available in order to do so. So here we'll just discuss what if we leverage a pre-existing image captioning model. So can the generated captions become more relevant? So for this purpose, we'll introduce a new model called BLIP. BLIP means bootstrapping language image pre-training. Bootstrapping language image pre-training. So this represents a novel modeling approach for unifying visual language understanding and generation. So what sets this BLIP apart from other vision language models is its effective utilization of noisy web data through caption bootstrapping. So basically in this process, a captioner generates the synthetic captions and a filter subsequently removes these noisy ones. So instantiate the BLIP processor for processing inputs and outputs. Basically, we can do the things like this. It has feed forward, cross attention, self attention layers. So we know all in most of the things, attention is all you need, which will focus on the relevant parts. So these multimodal language models, they have ushered in a new era for image captioning, enabling the machines to generate human-like descriptions of the visual context. So by seamlessly integrating this visual and textual informations, these models capture the intricate interplay between the vision and this language. Okay, thanks.